Welcome back to the deep dive. Today, we are wading into the vast, often intimidating, but absolutely crucial waters of modern software security.
Yeah.
For a long time, the security discussion, it felt like it happened right at the end of the development cycle.
Oh, absolutely. It was an afterthought.
The software was built, and then you tried to, patch all the holes.
Right.
It was the digital equivalent of building a high-tech armored vault, and then only realizing the blueprints for the door were published online after the bank opens.
It's more than just inefficient, though.
Yeah.
It's a fundamental mismatch with how modern software is actually built.
How so?
Well, today, an application isn't just one single product, right? It's a massive interwoven ecosystem of services, cloud dependencies.
And all those third-party components that update, hourly?
Exactly, hourly. So if you treat security as just some quality assurance check at the finish line, you have missed hundreds, maybe even thousands of opportunities for an attacker to get in.
Okay, so let's unpack this then. The source material we have today centers on a framework that has really defined this transition we're talking about.
Yeah.
The Microsoft Security Development Lifecycle, or SDL. And the SDL isn't, it's not the new kid on the block. It's been around for 2 decades.
Which is an eternity in tech.
Right.
And that longevity is precisely what makes it so fascinating to look at.
Okay.
I mean, think about the technological gulfs the SDL has had to span. It started in the desktop era of, Windows XP.
Wow, yeah.
And now it has to cover a world of hyperscale cloud, serverless functions, globally distributed microservices, and this incredible DevOps velocity.
So the core mission has stayed the same.
The core mission building fundamentally more secure software, that hasn't changed.
But the practices have had to.
Radically evolve? They had to.
So the practices have to continually evolve because the cybersecurity landscape, and specifically how software and services are built and deployed, is just constantly shifting.
It's getting faster, and it's incorporating way more external components. That's the essence of the SDL staying power.
I see.
It shifts security from being like a fixed checklist to being an integrated, continuous mindset that the entire engineering organization has to adopt.
And our goal today is to distill that framework's current state.
Exactly. We're going to break down the 10 key security practices that turn a traditional development workflow into a secure software factory.
So to understand the solution, we really need to understand the battlefield first.
Yes.
Before we get into those 10 practices, we need some context. Where exactly do the risks even appear in this modern, fast-paced life cycle?
That's the critical starting point.
Because if security is continuous, we have to know where to apply the pressure.
And the source material structures this really clearly. It identifies 4 distinct stages where security risks have to be actively mitigated. These stages basically define the scope for all 10 practices.
All right, let's walk through those 4 stages of risk. Where do we begin?
At the absolute beginning, the design stage.
Okay.
This first stage is purely conceptual. It's focused on the architecture. The risk here isn't bad code.
It's a flawed blueprint.
It's a flawed blueprint, exactly.
Yeah.
The fundamental security risk is designing the system in a way that just inherently allows attackers to easily gain unauthorized access to the workload or its data or other business assets.
I can see that. I mean, if you design a data pipeline that uses, say, one single highly privileged service account to move sensitive data around between 5 different microservices, you've basically built a weakness right into the architecture.
You've created a single point of failure. If any one of those 5 services gets compromised,
The attacker instantly gets access to everything.
all the data, exactly. So security has to be a primary consideration before a single line of code is ever committed.
So if the architecture relies on this idea of implicit trust between components,
Yeah, or if there's not enough isolation between different trust domains.
then no amount of secure coding or testing later on can fix that fundamental design flaw.
You've just created a really attractive target.
Okay, so once the design is solidified, we move into the actual construction. Stage 2, code. What are the concerns once developers actually get their hands on the keyboard?
The risk in the code stage really centers around the actual production of the artifacts.
Okay.
It's about writing, and maybe more importantly, reusing code, both your internal code and external code, that allows attackers to easily take control of the application.
And then they can perform unauthorized actions.
Exactly. Harming customers, employees,
Yeah.
systems, data. It could be anything from a traditional web attack like cross-site scripting to, deep memory corruption flaws.
So this is where we see all those traditional vulnerability classes, right? The classic mistakes, human error that leads to things like buffer overflows or injection attacks.
Yes, but a modern SDL acknowledges a far more insidious risk in this stage.
Oh.
And that's the integrity of the input environment itself. The source specifically highlights that the developer's environment has to be secure.
The developer's own machine.
Their machine, their internal tooling.
Yeah.
If any of that is compromised, an attacker can surreptitiously inject code changes, bypass the peer review process.
And have them approved and merged without the developer even knowing.
Without anyone knowing.
Wow. That's a profound shift.
It is.
It means the developer isn't just responsible for the quality of their code.
Yeah.
They're responsible for the security of the sandbox they're writing it in. The integrity of their workstation becomes mission critical.
It absolutely does. If that environment is compromised, you've essentially let the attacker sit shoulder to shoulder with your engineering team.
And every subsequent piece of code is immediately suspect.
Immediately. Which leads us directly into the third risk area.
Stage 3 is build and deploy. This is where the sheer velocity of CI/CD pipelines can introduce a ton of security friction.
People often call this stage the factory floor. And it is exceptionally high risk because it's so heavily automated and it relies on these machine identities that have enormous privilege.
So the core risk here is that the automated CI/CD process itself could be compromised.
Exactly. It could allow unauthorized users to alter the code or maybe even just the deployment scripts.
And then they can compromise the system silently.
Completely silently. We're protecting the mechanism of production itself.
Right. If a malicious actor can insert just one line into a build script on a server somewhere,
That line runs automatically.
it could bypass all human review and inject malware straight into the final product that goes out to millions of customers.
You're protecting the integrity of the assembly line. It demands securing the build servers, the artifact repositories, the automated testing tools.
And most importantly, the credentials used by those deployment agents, the machine identities.
Those machine identities we just mentioned, if a compromised pipeline distributes malicious code, the impact is global and it's instantaneous.
Okay. Finally, we reach the run stage. The code is now live, it's distributed, and it's operating out in the wild.
And the risk here centers on environmental failure.
Okay.
The environment that's running the code, be it a cloud tenant, an on-premises server farm, a mobile fleet, containers, it fails to follow security best practices.
So the application itself could be written perfectly. But it's sitting on, say, a virtual machine with an OS that hasn't been patched in 9 months.
Or the cloud firewall is misconfigured and it's wide open to the world.
I see.
Exactly. So mitigation here requires continuous, relentless adoption of well-established security baseline configurations for all the underlying infrastructure and the platform.
So it's about maintaining the security posture of the host environment.
Yes. Applying patches and ensuring that the platform's settings resist attack and abuse, not just the application logic itself.
So we've established these 4 critical risk stages: design, code, build, deploy, run, the 4 phases where a product is most vulnerable.
Right.
And the source makes it really clear that there's one fundamental philosophical framework that has to govern the security strategy across all 4 of them.
It does.
And that framework is zero trust.
Zero trust is the necessary pragmatic response to the reality of the modern perimeter.
Which is porous, to say the least.
It's basically gone.
Because applications now rely on cloud services, mobile access, third-party APIs, the old model of trust anything inside the firewall is dead.
So it has to be thrown out.
Completely. And so all 4 stages of development and operation must strictly follow zero trust principles. It's the governing security model that the SDL then implements tactically.
Okay, let's break down those core tenets, because they aren't just buzzwords, right? They fundamentally change how engineers approach security planning.
They really do.
The first one is maybe the hardest to accept. Assume breach.
Assume breach is not pessimism. It's resilience planning.
Okay.
It just means that your security planning has to operate under the constant assumption that systems will eventually be compromised.
So you're designing your system from the very beginning, not just to prevent the attack,
but to limit the blast radius when the breach inevitably occurs.
So if I assume breach during the design stage, stage 1, I don't just think about how to stop an attacker from getting in.
No.
I think about what they can do once they are in. Precisely. You implement strong segmentation, you limit their lateral movement, You ensure encryption applies everywhere.
So if one container gets compromised,
The hacker shouldn't be able to just pivot easily to the database container.
because they're microsegmented.
And they require explicit verification to talk to each other, which leads directly to the second tenet. Explicitly verify trust.
Trust is never implicit.
Never. Every single request, every identity, every device, every component must be rigorously verified before access is granted.
And this holds true regardless of where it's coming from.
It doesn't matter if it's an external customer or an internal microservice running on the same Kubernetes cluster. We verify against context. Who is this? What device are they on? Where are they accessing from?
And why do they need this specific piece of data right now?
And does their risk score look acceptable? All of it.
I think this is where a lot of organizational friction comes in. An engineer sitting at a corporate desk might argue, hey, I'm internal, I should be trusted implicitly.
And that perspective is precisely what the SDL is designed to dismantle.
Right.
In a zero-trust environment, that internal access is treated just as suspiciously as external access. If a developer needs access to a secure build tool,
Part of that code stage integrity.
they must prove their identity and the integrity of their device explicitly, every single time.
And that stops an attacker who has compromised a legitimate internal device from just strolling through the environment undetected.
It does. And that rigorous verification feeds into the third crucial principle: grant least privilege.
The principle of minimum necessary access.
The bare minimum. Users, machine, and service identities, which are so important in the build-deploy stage and application components, should only be granted the absolute minimum access required to perform their specific function, nothing more.
So if a web app only needs to write logs,
It must not have permissions to delete configuration files or change user passwords.
and limiting that privilege severely restricts the attacker's ability to move laterally if they do manage to compromise something.
It's the safety valve. It ensures that assumed breach doesn't just turn into a total system failure.
Absolutely. Okay, so as we move into the 10 practices, you should keep this framework in mind.
Yes.
These 10 steps are the SDL's concrete tactical methodology for building and operating software under this heavy mandate of zero trust across all 4 of those risk stages.
That's the perfect way to frame it.
Let's transition into the practices themselves, starting with the foundational steps that govern the entire operation. Practice 1.
Practice 1. Establish security standards, metrics, and governance.
This sounds like the bureaucratic backbone of the whole process.
It kind of is.
I imagine for an organization as big as Microsoft, defining these standards and metrics is just so important for consistency.
It's the rules of the road. I mean, without clear, measurable security standards and governance, every engineering team just operates in a silo.
Which leads to a chaotic and inconsistent security posture.
Exactly. Governance provides accountability and it enforces uniformity.
So how does the SDL suggest you quantify success? I mean, it's easy to count bugs, but how do you measure the effectiveness of a proactive security program?
You measure process maturity and you measure execution speed.
Okay.
So metrics will often track, say, the percentage of projects that successfully complete a mandatory threat model review. That's practice 3. Or the speed, the mean time to mitigate, once a high-severity vulnerability is found.
You also track adherence to security baselines.
You do. And governance ensures that if a team fails to meet a defined metric, say their code review coverage is too low, there's a clear and required remediation path.
Which prevents security from becoming optional.
Or, just a suggestion, it gives the security team the organizational muscle to enforce these policies across potentially thousands of developers globally.
So it's not just about compliance, it's about defining the acceptable speed of failure response and forcing teams to adopt standardized, secure processes.
Precisely. It sets the bar and holds everyone accountable to it, ensuring that security maturity doesn't just rely on the enthusiasm of a single team lead.
It's an organizational mandate.
Yes.
Okay, that leads to practice 2. Require use of proven security features, languages, and frameworks.
The underlying philosophy here is just its efficiency through standardization.
Right.
Developers, in the rush of innovation, they often try to customize or build their own tools, especially for security functions like authentication or input validation.
Or encryption. And we know that custom security solutions, especially custom crypto, are almost always dangerously flawed.
Almost always. The core idea is simple. Leverage existing, vetted, and well-supported technology.
Don't reinvent the wheel.
Don't reinvent the wheel badly. By requiring the use of proven security features, languages, and frameworks, you dramatically reduce the chance of common mistakes turning into critical exploits.
So this is a direct mitigation against those common coding errors we talked about in the code risk stage.
It is. So instead of letting every team implement their own token validation library,
The organization mandates a single, approved, internally managed library that wraps the secure primitives.
that's the operational reality.
Mhm.
And it frees the security organization from having to audit 100 different variations of input sanitization logic.
Right.
They only need to audit and maintain that one approved security feature. It removes ambiguity for the developer, and it consolidates the security team's focus.
Okay, that makes sense. Practice 3. Perform security design review and threat modeling. This practice is the direct mitigation strategy for the risks we identified in that first design stage.
It is.
It's building the security thinking right into the blueprint phase, asking the hard questions when the system is still just a bunch of boxes and arrows on a whiteboard.
This is often cited as the most critical and the highest ROI practice in the entire SDL.
Really?
Threat modeling is a proactive adversarial analysis of the system architecture. You're trying to identify threats, vulnerabilities, and required countermeasures before any implementation begins.
So you map out the data flows, identify who and what needs access.
Determine the trust boundaries, and then you hypothesize attack vectors.
You know, I still see development teams, especially agile teams focused on rapid delivery, try to skip this entirely.
They do.
They see it as bureaucratic overhead that slows them down. Why is it so hard to get engineers to sit down and think like an attacker at that design stage?
Well, it requires a different mindset, and sometimes organizational pressure just prioritizes shipping features over foundational integrity. But the financial imperative should be impossible to ignore.
Okay.
I mean, if we connect this to the bigger picture, fixing a flaw discovered during a design review takes, what, an hour in a meeting to adjust a diagram?
Right.
Fixing that identical flaw after the system is deployed and running a flaw that might require rewriting authentication protocols or data pipelines.
Can cost 100 times more in developer time, testing delayed features.
100 times more.
Yeah.
Threat modeling shifts that expense curve dramatically toward the preventative side. It's the cheapest place to fix a security bug.
Can you give us an example of a common output of a threat model? What does it actually produce?
A good threat model identifies assets, the sensitive data you're protecting, and then it models the threats against them. So, for example, if your asset is customer PII,
Personally identifiable information.
right, the threat model might reveal that an internal administrative tool, which wasn't initially seen as critical, has a direct, unencrypted path to that data.
So the output isn't fix bug X.
No. The output is mandate multi-factor authentication for that admin tool and enforce TLS 1.3 encryption on that data channel. It provides a list of controls that have to be built into the system design long before the first line of functional code is written.
Okay, practice 4. Define and use cryptography standards.
This follows those principles of standardization again. It isolates cryptography as a specialized high-stakes area that really demands organizational oversight.
It has to be isolated, doesn't it? Because data protection is foundational to that assume breach tenet of zero trust.
Absolutely. Data has to be protected at rest and in transit. And without standardization, you just inevitably introduce the weakness of fragmentation and outdated algorithms.
So if the organization doesn't standardize, what are the most common risks you see?
Oh, the use of outdated algorithms, insufficient key lengths, insecure modes of operation.
Right.
Developers, maybe using older tutorials they found online, might unknowingly deploy an encryption method that was secure 5 years ago, but is trivial to break today.
So standardizing cryptography prevents that.
It prevents the use of weak, outdated, or bespoke, home-rolled encryption methods. The SDL mandate here involves specifying which cryptographic algorithms are approved, what key lengths are acceptable, and critically, how keys must be managed, rotated, and secured.
Which ties back into practice 6, securing the engineering environment.
It does. This is the policy-level enforcement of what you discussed conceptually during the design risk stage. You're ensuring the locks in your digital assets are not only robust, but uniformly applied across the entire organization.
So that data remains protected even if the surrounding infrastructure or the application code is momentarily compromised.
Exactly. It reduces the impact of a breach, just like zero trust mandates.
All right, so we've moved past the policy and design phases. Now we are deep in the dynamic phase of production, the code and build deploy stages.
Yes.
And this is where the sheer velocity and interconnectedness of modern development creates these massive new security headaches.
It really does. Which brings us to practice 5. Secure the software supply chain.
Okay.
What's radically different about software development now compared to, say, 20 years ago is the volume of imported code.
Right.
The modern application relies so heavily, sometimes overwhelmingly, on open source software and external dependencies. Your application is no longer just your code.
It's a vast, sprawling ecosystem of components you just consume.
You consume them, and this practice directly confronts the inherent trust problem that arises when developers are pulling in hundreds of libraries from thousands of external maintainers.
So security has to extend far beyond your own proprietary code base.
Far beyond. Every dependency, every library, every upstream component is a potential vector for an attack.
Because if one library deep within your dependency tree gets compromised,
Either through a malicious injection or just by exploiting a known bug, your entire application is compromised.
So securing the supply chain really means having strict procedures for vetting and monitoring all of those external dependencies.
It does.
We're talking about generating and managing a software bill of materials, an SBOM. Can you clarify what an SBOM is and how it's actually used?
An SBOM is essentially an inventory. It's a detailed hierarchical list of all the components, their versions, their origins, their licenses that make up your final software product.
But it's not just a passive list, is it?
No, it's an active security tool. When a critical vulnerability is discovered in, say, a really common logging utility,
Okay.
the security team can immediately query the SBOM to identify every single application across the entire organization that uses that specific vulnerable component,
And that allows for targeted, rapid remediation.
instead of a slow manual hunt through every single repository.
Exactly. It turns a potential zero-day catastrophe into a manageable incident.
And the SDL mandates these strict consumption processes, often called a secure supply chain consumption framework, to make sure you vet, catalog, and continuously scan all your dependencies.
The crucial insight here is that you are outsourcing your security integrity to every library maintainer you trust.
You are. And Practice 5 forces you to formalize that trust relationship and monitor it constantly.
All right, practice 6, secure the engineering environment.
This is a big one.
We identified earlier that if the developer's sandbox is compromised, the code that comes out of it is useless from a security standpoint.
Right.
So this practice is about applying that zero trust, explicitly verified tenet internally to the development factory itself.
And this is such a high priority practice today because state-sponsored actors frequently target engineering environments.
Why bother exploiting a flaw in the final code?
When you can compromise the source code before it's even reviewed.
Yeah.
If the actual environment where developers write and build code is compromised, the workstation, the internal network, the build server, the resulting software is compromised by design.
So this means things like segmenting the development network, enforcing strong device integrity checks, and ensuring rigorous access control even for internal systems.
Absolutely. Think about the keys to the kingdom.
Right.
The build environment houses the most sensitive assets. The source code repositories, the signing keys used to cryptographically verify the software's authenticity.
And the deployment credentials as machine identities.
All of it. These have to be treated with the highest security priority.
Because if an attacker compromises a single build server, they can use its trusted identity to sign malicious code and push it straight out to customers.
Bypassing all subsequent security checks. This is the exact scenario we saw in major pipeline attacks over the past few years.
So that's the direct path to that build and deploy risk scenario we discussed.
It is. And Practice 6 dictates that we have to apply the zero trust principle of least privilege to those service identities.
Does the build script really need permissions to access the production database?
Typically, no. It only needs permissions to build and sign. Limiting the scope of those machine identities is arguably one of the most effective defensive measures a modern SDL can mandate.
Okay, that brings us to practice 7, perform security testing.
Right.
So we've governed the process, we've secured the supply chain, we've secured the environment. Now we check our work before it goes live. This is the validation step.
This practice is the practical check. It verifies that the standards you set early on and the countermeasures you designed in Practice 3 were actually implemented effectively.
It's the systematic application of tools and techniques to find vulnerabilities in the code and the running system configuration.
Yes.
But in a world of continuous delivery, testing can't be a single quarterly event, can it?
No way. It has to be automated and integrated.
It has to be continuous.
It must be. We're talking about integrating several layers of testing directly into the development pipeline. You have static application security testing, or PADT,
Which checks the source code before it runs.
right, looking for known insecure coding patterns. Then you have dynamic application security testing, or DAST, which checks the running application.
Simulating attacks against the deployed components to look for real-time vulnerabilities.
Exactly. So SAST might catch the insecure use of a library, while DAST might catch a misconfiguration of the operating environment or how the application responds to unexpected inputs.
That's a good distinction.
And critically, these automated tools act as gatekeepers.
Okay.
If your automated scans find a critical vulnerability, that code should be prevented from ever moving to the build and deploy stage. It enforces compliance automatically.
So testing acts as the necessary check against assumptions and human error, confirming compliance before the final distribution.
It's the moment of truth for the system's resilience against the threats you identified.
Okay. We have successfully navigated design, code, and build deploy. The software is signed, shipped, and it's live. But security cannot end at the release date.
No.
Which brings us to the operational phase, the run stage, which demands perpetual vigilance.
It does, which is Practice 8, Ensure Operational Platform Security.
This practice directly addresses the run risk stage.
It does. The moment the software is deployed, a new, ongoing phase of security maintenance begins. This practice focuses entirely on maintaining the security posture of the host environment where the code actually lives.
So the application might be flawless.
But if its foundation is weak, the entire system is vulnerable.
So this is infrastructure hardening, patching, and making sure that everything that hosts the application is configured securely.
Exactly. It's securing cloud configurations, ensuring servers, containers, and serverless functions are continuously patched, hardened, and that access policies are correctly applied. A massive source of vulnerabilities today is configuration drift.
Configuration drift, that sounds bad.
It is lethal.
Yeah.
Imagine your security team defines a baseline that mandates all external connections have to use the strongest encryption, TLS 1.3. But a rushed administrator, maybe making a manual change to deploy a new feature, accidentally rolls out a new load balancer that defaults back to an older, vulnerable protocol like TLS 1.1.
That's configuration drift.
That's it. And Practice 8 dictates that you must have automated mechanisms in place, tools for configuration management, infrastructure as code, to continuously validate that the live environment adheres to the security standards you established way back in Practice 1.
So if you design the system for least privilege back in Practice 3, then Practice 8 ensures that the running system stays in that least privilege state.
Even as new services are added or configurations are updated, it requires relentless automated validation.
Because modern infrastructure is so often ephemeral, right? Containers are spinning up and down in minutes.
You can't rely on manual checks. You need the platform itself to enforce the security baseline instantaneously.
Makes sense. Okay, Practice 9. Implement security monitoring and response. Since the zero trust philosophy mandates we assume breach, this practice is the absolute necessary corollary. If we assume we're compromised, we have to be able to spot the attacker immediately.
And react with surgical speed. Security is a continuous detection and reaction loop. No amount of proactive security can prevent every single attack.
So this practice requires implementing robust logging and monitoring systems.
Right, often called SIEM and SOAR systems. And it requires establishing clear, tested procedures for incident response when a vulnerability or a breach is actually detected in the running environment.
Can you elaborate on the response component? What does that actually look like in a highly automated environment?
Well, it starts with having comprehensive audit logs that track every significant action, user activity, system changes, access attempts. That's a key tenet of explicit verification.
Right.
The SIEM system aggregates these millions of logs and applies analytics to generate meaningful alerts based on anomalous behavior.
But the technology is just the detector.
It is. The response is the crucial human and automated action.
And if a breach is detected, the window of time for the attacker to move laterally is often measured in minutes, right?
It can be. That's why the response has to be defined and practiced ahead of time. Automated response, the SOAR part, might instantly isolate a compromised user identity or shut down a suspicious connection.
Or roll back a misconfiguration.
Exactly. The operational team needs clear, defined procedures for containment, eradication, and recovery. They need to know exactly who to call and what steps to execute at 2 a.m. to minimize the attacker's window of opportunity.
And that process then feeds crucial real-world learning back into the entire SDL.
It does. which leads perfectly into the last practice.
Practice 10. Provide security training.
This practice closes the loop entirely, acknowledging the human element.
Because all the technology, the governance, the rigorous design, it all collapses if the people executing the steps don't understand or follow the process.
It's essential for long-term organizational security maturity. Training ensures that the evolving SDL, the new learnings from breaches from Practice 9, updated best practices, new tooling, all of it is properly understood and applied by everyone.
Developers, engineers, product owners, even executives.
Everyone. It combats that organizational inertia, the "we've always done it this way" mindset.
And it ensures that the lessons learned from recent incidents are actually internalized and implemented in future projects.
Exactly. Security threats evolve incredibly fast. What was a secure practice 5 years ago might be a critical vulnerability today.
So continuous mandatory security training ensures that the organization's collective knowledge base just keeps pace with the current threat landscape.
And with the evolving SDL practices themselves, it's the critical mechanism that ensures that future projects start securely, integrating the learnings from practices 7, 8, and 9 right back into the initial design stage.
Without this practice, the security culture just stagnates.
It dies on the vine.
That was an incredibly detailed and structured deep dive. We've taken the complexity of the modern software development cycle design, code, build, deploy, run, and mapped 10 systematic practices against them, all underpinned by that demanding philosophy of zero trust.
The power of the SDL is really how it forces that philosophical shift.
Right.
Security is no longer a department. It's a non-negotiable quality attribute that's integrated into every single step. It demands governance and accountability, foresight, and adversarial thinking.
Disciplined technical execution and perpetual operational vigilance.
That's a great summary.
So what does this all mean for you, the listener? Whether you're a developer trying to improve your craft, a product owner evaluating risk, or you're just curious about how secure technology is truly built today.
Understanding these 10 steps provides a really powerful framework.
You can use this to evaluate the security maturity of any organization.
You can see that security touches governance, design, the supply chain, and continuous operations. It's everywhere.
And critically remember that the SDL isn't static.
Not at all. It is a living methodology. As soon as a major new attack vector emerges, say a vulnerability in a core container orchestration tool, the training, the standards, and the required security controls have to adjust immediately.
It's a process of continuous defense modernization.
Yes.
We spent a significant amount of time detailing how practices 5 and 6 focus specifically on securing the development pipeline itself.
Right, driven by that zero trust mandate to explicitly verify the integrity of the code source and the tools used to assemble it.
And it highlights that the integrity of the process is just as important as the code itself.
It absolutely is. And this raises an important question for you to mull over, specifically concerning that high-risk build and deploy stage.
Okay.
If zero trust requires explicit verification, even internally, and if we know securing the CI/CD pipeline is critical, what is the single most critical and often overlooked identity that needs rigorous verification within a modern development organization to prevent malicious alteration of code?
And it's not the human developer logging in with MFA.
No, it's the automated service account, the machine identity that runs the CI/CD pipeline. That single identity possesses the authority to pull source code, run the build process, sign the resulting artifact, and push it directly to production.
Compromising that one machine identity
Grants an attacker absolute, silent, and mass distribution capability. Securing the integrity and minimizing the privilege of that pipeline identity is the ultimate test of the modern security development lifecycle.
If you can't trust the robot building the software.
You can't trust the software itself.